Okay, so hi, welcome back. Last video, we actually talked about how to use a little bit of the OpenFOAM namespace. Now, let's say there are some functions you want to test within OpenFOAM. Like I said in the last video, there are there's the linearEqn.H that you want to test out, and of course there are other equations like cubic and quadratic as well. Okay, so let's try including our linear equation. Okay, and you don't have to actually specify the file path because it's already specified for you in the make file. And once you have your fvCFD. So let's do sandbox2.c. Open it up. And let's take a look at linearEqn.H. Okay, this is a very simple thing. Okay, you're supposed to give it two scalars and you're supposed to run some things with it. So let me show you some things. Okay, one of these things is that it uses the namespace form. Okay, so that's what you need to do. I mean, that's what it's doing. It's not what you need to do. So it declares a new class, and the public members, you have these constructors. So to initialize it, you use these constructors. Now you see this thing inline here. I already kind of shown. I think in the last video I would have shown you the links as to what this inline thingy actually means. But for the most part, just for your understanding of coding, the most basic understanding, you can just sort of ignore this because all right, the constructors are just functions. Okay, inline is just a way you actually compile those functions, one way. But you can see how you can actually start defining your object using your class here. Remember, the class is linearEqn, and to create an instance of this class, we have to declare an object over here. I assume you're already pretty familiar with this. Okay, so your constructor is here to initialize your object. So there are three ways you can do it. You can do it without declaring anything. You can start with a 0, okay, a form 0, or you can start it with a scalar or two scalars. Okay, the first scalar is a, the second scalar is b. Okay, so a is here, a times x equals to b. A times x plus b equals to 0. Right. A times x plus b equals to 0. Okay, so you start it with two scalars. Now, I'm going to assume, well, normally, of course, I'm going to assume, I'll just pretend that this include is actually included in fvCFD.H. But in actual fact, it's not. But how would you do it? Okay. Normally, you need to type this out first, right? You need to type the class. What's the class here? Okay, class is called linearEqn. So let's write linearEqn. So I will just call this equation1. And I want to put in two things, okay? I want to give two scalars to it. So let's say I want the scalar 2 and 7. Okay. So let's just give it two values, 2 and 7, and see whether it works. Remember, always have your semicolon. So equation 1 is now of the class, supposedly of the class linearEqn. And I want to then get the value of this equation 1 at, let's say, x equals to 5. Now, the thing is, while in the comments it says ax plus b equals to 0, okay, the actual equation you're solving for is y equals to ax plus b. Okay, y equals to ax plus b, or y equals mx plus c, however you want to call it. All right. Okay, so this is just what we are doing. Okay. So anyway, okay, what we are defining here are these functions. Okay. So how do you read this? Okay, remember over here, the inline is just a way you sort of define your function or compile your function later. A linear equation here is the function that you want to get. Okay, so these are the constructors which the function name is the same as the class name. Okay, so that you can initialize your own object. Okay, it's linear equation. Then what do you want to do with linear equation? I want to find the value at maybe x equals to 5. How will you do it? Okay, so what I'll do is maybe I'll say a equals to equation 1 dot value at x equals to 5. This is how you would do it. Okay, remember we have linear equation. We just define an object. This object represents a linear equation with y equals 2x plus 7. If I'm not wrong, your first scalar defined is a, your second scalar is b. So a is the coefficient of x, b is the constant, so y equals 2x plus 7. So if you want the value at x equals to 5, then you just access one of the functions. So you use the object, then you dot something. Okay, when you dot something, that's actually looking for the function. Now this function here, this is the function here, and what it will do is that it will return a scalar value over here. Scalar. Okay, it has to do with scalar. Okay, now let's try compiling this file, and likely it will just give you an error. Okay, most likely it will give you an error. So you'll compile the dependencies first, and then you'll say, okay, you'll complain, linear equation was not declared in this code. Do you mean linear underscore h? So what you need to do is just also, as with every other class, you need to do a manual include. Okay, you need a manual include. So what do you need to include? Linear equation.h. So I'm just going to put it here. Good. And linear equation.h. Let's try running. So let's wmake, and you're gonna get another error. That's the wrong way to do it. I'll show you why in a bit. Oh, is it? Okay, maybe it's okay. Maybe it's okay. Sandbox2. Okay, sandbox2.c. Alright, so these two includes are okay. So let's run sandbox2. Okay, looks okay. And we have not gotten ourselves any feedback yet. Okay, let's output these values first. How do we do? We use info and y equals to. Okay, normally you can actually put your scalars in here, so you can do it. You know, we can actually change this code to become a bit more versatile. But for now, this will have to do. Okay, so this is y equals 2x plus 7, and okay. And then you can say info at x equals to 5, y equals to, and then you can just return the value of a. And inline that. So you can wmake again. Alright. And you'll be okay. Sandbox2. So at x equals to 5, y equals to 17. Makes sense, right? Okay, 2 times 5 is 10, plus 7 is 17. Very easily verifiable. So that's how you use it. Now the thing is that I think sometimes you don't know. You may or may not have this include here. Okay. What I was saying just now when I said, oh, there could be a mistake if you put your include in the wrong place. This is what I'm talking about. If you put your include in your integral int main, this is what will happen. Okay, if you try wmake. Okay, so you have a lot of errors. What's actually going on? If you try and take a look at this try and look at this. Okay, so in file included linear equation H50, it says error, namespace definition is not allowed here. Okay, again, namespace definition is not allowed here. Why? Okay, if you look at this, you see this part that says, I want to use the namespace form. Yeah, I want to use the namespace form. Okay, and this thing, you can only do it before you start your int main. All right, so before you start your int main. All right, so the compiler actually complains to you because you're trying to use your namespace form in your int main. All right, in your int main, in this part, you are trying to use your namespace form. But in fvCFD.H, you already force the main function to use the namespace form. So you can't, like, you know, declare one namespace and then use another namespace, basically. Probably that's why there's some error there. There's some conflict when you try to confuse the compiler, say, I want to use this namespace A, I want to use this namespace B. Maybe you get confused. Okay. Okay, and why is it okay to include it outside? Okay, you can do it before the fvCFD.H or after, because you see, once you use it, you have this thing called namespace form, and after you declare all your classes, you have this thing. You might have this n namespace form dot here. I mean n namespace form over here. Right? There's also this linear equation I.H, which you can look. Linear equation I.H. If you go all the way to the bottom, yeah, it looks like it still uses the namespace form. Okay. So I guess when you do this include, you are already using the namespace form. Yeah, but basically you're supposed to define all your namespaces maybe before you start your int main. Okay. And notice over here you don't have your IO stream and everything anymore. It's already being included in fvCFD.H. So it's very convenient for you. All right, so what else? Okay, we already defined two scalars. Okay, we can even evaluate the derivative. Okay, so let's get the derivative, and then the error I'm not going to bother. Let's also take a look at the roots. Okay, so let's put this part as, okay, get derivative. Okay, and again, the way to do it is we can do info derivative or dy dx, yeah? dy dx, so I like to put it, equals, right? At maybe x equals to 5 equals this. Then what do? You can just use the class derivative class. Okay, so let's put equation 1 dot derivative at x equals to 5. Again, of course, we can use variables to do this to make it more versatile, but just for demonstration purposes and to make it speedy, expedient or faster, I'll just use numbers. See how much time. Okay, it's about 14 minutes here. All right. Now this dy dx at x equals to 5 equals to this n line here. And why do I have a double E? All right, I'll just derivative E. Okay, let's do wmake again. All right, and let's do sandbox 2. Okay, dy dx at x equals to 5 equals to 2, because no matter where x is, the derivative is the same. Okay. Now last one I want to do is the roots. Okay, so I'm pretty sure you're kind of getting the hang of it by now, watching me do it so many times. Hope you can go and practice on your own. I'll give you the GitHub file. YouTube C OpenFOAM is the same as the one I use for my OpenFOAM C++ for OpenFOAM beginner C++ for OpenFOAM. Yeah, it's the same GitHub as the playlist. So let's say, let's do roots. Okay, now equation 1 dot roots. Okay. So this is where you will have your roots. Okay, it is some it is not exactly a scalar because it's now of the, it will be given the class, I mean it will be given the, instead of a integer, because okay, you have a class type integer, I mean the return type is integer. This one is a return type of roots and the function is called roots. Okay, I assume you're familiar, so I'm not do too much. Okay, so the root over here we expect it to be wherever y equals to 0. Okay, y equals to 0 and x equals minus 3.5. So this should be this should return us minus 3.5. Okay, now let's do sandbox 2, and you can see the roots are at x equals to minus 3.5. Notice now you'll see that there are some brackets around, which means it's not a scalar anymore. Maybe it's some sort of vector or something like that, but the long and short of it is that you cannot just do math between scalar, the type scalar and the type root. It will not compute properly. Okay, but this just to acquaint you, just to throw in a little bit more. Let me throw in the cubic equation. Okay, let's include the cubic equation. We have a cubicEqn.h. Okay, that cubicEqn.h. Okay, so you will again see value, derivative, and roots. It's basically the same. Okay, so there are four scalars you need to put in. Okay. So I'm not going to elaborate how they sort of do all the calculations. So these are the cubic equations with this form: ax cubed plus bx squared plus cx plus d equals to 0, or more likely equals to y. Okay, so let's do it. Same thing. Okay, once you get the hang of it, it's pretty straightforward. So let's include one more cubic equation dot h. Okay, cubic equation dot h. Include cubic equation dot h. We can use the same thing as well. Okay. So let's do this. Cubic equation 2. Then we need to give it 4 numbers. So maybe I'll just do 1, 2, 3, 4. Of course, you can have scalars or some other variables there, whatever you want. 1, 2, 3, 4. Remember, always put your semicolon. Be like me, I forget a lot. Okay, cubic equation, and let's again let's do cubic equation value at x equals to 6 or 7. Let's do x equals to 7. Info, let's do equation 2 dot value at x equals to 7. Right. Second thing, let's do dy dx, right? Info. Okay. Dy dx at x equals to, let's try 0 and x equals to 7, because now your gradient is actually dependent on where x is. Okay, it's a cubic curve. So our gradient will differ depending on where x is, right? Okay, so this one, the first one is for x equals to 0. Second one is, okay, at x equals to 7. dy dx equals, okay, we just do equation 2 dot derivative 7. Okay, and 9. Let's double make this to just check whether we get any syntax errors. Okay, so no syntax error so far. Okay, so how do I know? Because I see this inline scalar value, inline scalar derivative. Then I have my roots function here as well. So let's do sandbox 2. Okay, so we can see that cubic equation value at x equals to 7 is 466. Okay, if we want to check, of course, we can use LibreOffice, Excel, whatever. 1, 2, 3, 4. So remember ax cubed, bx squared, cx plus d. So, right. How do I do this? O f x to the power of n. This one is n equals to. Okay, let me put x here. Okay, n 1 of 3, 2, 1, 0. Okay. So x is maybe let's put 7 here. So this will be x cubed. This will be x squared. This will be just x, and this will always be 1. Okay, so you want to sum them up. Like so, you get 400 at x equals to 7. Okay. Okay, so OF times x to the power of n. Then you have just this times this 343, so on and so forth. You put this over 466. Let's check the output. It indeed is 466. For dy dx, I'm not going to do the derivatives in front of you. It's kind of meaningless. Okay, I just assume it's correct. Right? You don't have to check every single thing. I assume the code developers did a good job of that. Right. So yeah. Let's do one more, and then we'll call it a day. So let's go to sandbox 2.c, and let's find the roots of this equation. Info roots. Okay. So how do we do it? Equation 2.roots. Okay. Okay. Double make. And then we'll have a sandbox to put. You can see the roots here are minus 1.65, minus 0.174, 1.54687. Don't believe me, you can just go on wolfram. Okay, maybe I won't be lazy. Let me go and wolfram and find. Wolfram. Okay. That's the roots of polynomial x cubed plus 2x squared plus 3x plus 4 equals to 0. Okay, it will give you some funny number. Oh, it looks like we have some imaginary roots as well. Did I have it wrong? Okay. Solve. Okay, looks like we have a complex conjugate pair. Okay, complex conjugate pair and one of these real roots at minus 1.5 something. Okay. Right, let's see what we have here. Minus 1.65, this is what we have. Minus 0.17 seems to be this thing here. which seems to be the real part of these roots. 1.547, I don't know where it is from. Okay, so I guess it's, you know, not all perfect. Okay, always good to check. I think don't be lazy. That's the moral of the story. Okay, but no. Yeah, I don't know how the algorithm actually winds up getting this at this point in time. I mean, I can always find out, but as for now, I don't really feel like doing anymore. I've already given you some some intro into how to use some of the classes in OpenFOAM. Use at your own discretion. Okay, use at your own discretion. You still need to check it to see whether it works. Okay, so the two of the classes are already demonstrated for you, the linear and cubic equation.h. And you can use this to calculate simple things. Okay, you don't have to use OpenFOAM libraries to do OpenFOAM per se, but well, yeah, all the basic classes are there. You can use it. All right, so that's all I will have here. At least we gone through the scalar classes and some of the very basic classes in OpenFOAM. Hopefully, now you're a little bit more familiar with the foam namespace, the info, the way you print it using the info, foam info, and of course, some of the classes inside OpenFOAM. This is how you can use them. All right, I'll see you next time. Bye-bye.